Welcome. Today we're diving into the fascinating world of unsupervised learning algorithms. Unlike supervised learning, where models learn from labeled data, unsupervised learning works with data that has no labels at all. This approach helps us uncover hidden patterns, groupings, and structures within datasets that might otherwise go unnoticed. Throughout this video, we'll explore what makes unsupervised learning unique, why it's important, and how it's used in real-world scenarios. Let's start by understanding the core idea behind unsupervised learning and how it differs from other machine learning approaches. Supervised learning is a type of machine learning where algorithms analyze and interpret data without any predefined labels or categories. The main goal is to find patterns, similarities, or differences within the data. This method is especially useful when we don't have prior knowledge about the data's structure. For example, unsupervised learning can help group customers by purchasing behavior or detect unusual activity in network traffic. By letting the algorithm explore the data freely, we can discover insights that might not be obvious at first glance. One of the main differences between unsupervised and supervised learning is the presence of labels. In supervised learning, each data point comes with a label, guiding the algorithm to learn the relationship between input and output. In contrast, unsupervised learning works without labels, so the algorithm must find structure on its own. This makes unsupervised learning more exploratory and often more challenging, but it also opens the door to discovering new and unexpected patterns in data. Supervised learning algorithms are used in a wide range of applications. For instance, they're essential in customer segmentation, where businesses group customers based on purchasing habits. They're also used in anomaly detection, such as identifying fraudulent transactions or unusual network activity. Additionally, unsupervised learning helps in organizing large collections of documents, images, or other data types by finding natural grouping. These applications highlight the versatility and power of unsupervised learning in making sense of complex datasets. Clustering is one of the most popular techniques in unsupervised learning. The goal of clustering algorithms is to group similar data points together based on their features. This helps us identify natural clusters or groupings within the data. Clustering is widely used in market research, image analysis, and even in organizing social networks. Let's take a closer look at some of the most common clustering algorithms and how they work. K-means is a simple yet powerful clustering algorithm. It works by dividing data into a predefined number of clusters, called K. The algorithm assigns each data point to the nearest cluster center, then updates the centers based on the points assigned. This process repeats until the clusters stabilize. K-means is widely used because it's efficient and easy to implement, making it a go-to choice for many clustering tasks. Hierarchical clustering builds a tree-like structure of clusters, known as a dendrogram. It starts by treating each data point as its own cluster, then gradually merges the closest clusters together. This process continues until all points are grouped into a single cluster. Hierarchical clustering is useful for visualizing relationships between data points and understanding how clusters are formed at different levels. BSEAN, which stands for Density-Based Spatial Clustering of Applications with Noise, is a clustering algorithm that groups data points based on density. Unlike K-means, it doesn't require specifying the number of clusters in advance. DBCN can find clusters of arbitrary shape and is especially good at identifying outliers or noise in the data. This makes it a powerful tool for tasks where clusters are not well separated or have irregular shapes. Mean-shift is another clustering algorithm that works by shifting data points towards the densest area in the feature space. It doesn't require specifying the number of clusters beforehand. Instead, it automatically finds the number of clusters based on the data's density. Mean-shift is particularly useful for image segmentation and tracking objects in videos, thanks to its ability to adapt to the data's structure. Gaussian mixture models, or GMMs, are probabilistic models that assume data is generated from a mixture of several Gaussian distributions. Each cluster is represented by a Gaussian, and the algorithm estimates the parameters of these distributions. GMMs are more flexible than K-means because they can model clusters with different shapes and sizes. They're widely used in speech recognition and image analysis. Clustering algorithms are everywhere in our daily lives. For example, streaming services use clustering to recommend movies or music based on your preferences. Retailers group customers to tailor marketing strategies, and social media platforms organize users into communities. These real-world applications show how clustering helps businesses and platforms deliver personalized experiences. Another important area in unsupervised learning is dimensionality reduction. This technique helps simplify complex datasets by reducing the number of features while preserving important information. Dimensionality reduction makes data easier to visualize and analyze, especially when dealing with high-dimensional data. Let's explore some popular dimensionality reduction algorithms and their uses. Principal component analysis, or PCA, is a widely used dimensionality reduction technique. PCA transforms the original features into a new set of variables, called principal components, which capture the most variance in the data. By keeping only the most important components, PCA reduces the dataset's complexity while retaining its essential structure. This makes it easier to visualize and analyze large datasets. TSNE, or T-distributed stochastic neighbor embedding, is a powerful tool for visualizing high-dimensional data. It maps data points into a lower dimensional space, usually 2 or 3 dimensions, while preserving their relationships. TSNE is especially popular for exploring complex datasets like images or gene expression data, making patterns and clusters easier to see. Autoencoders are neural networks designed to learn efficient representations of data. In dimensionality reduction, autoencoders compress data into a lower dimensional space and then reconstruct it. This approach is especially useful for handling complex, nonlinear data. Autoencoders are widely used in image compression, noise reduction, and feature extraction tasks. Feature extraction is a key part of dimensionality reduction. It involves transforming raw data into a set of meaningful features that capture the most important information. By focusing on relevant features, we can improve the performance of machine learning models and make data analysis more efficient. Feature extraction is widely used in fields like computer vision and natural language processing. Association rule learning is another important unsupervised learning technique. It's used to discover interesting relationships or associations between variables in large datasets. A classic example is market basket analysis, where retailers find products that are frequently bought together. Association rules help businesses make data-driven decisions and optimize product placement or promotion. The apiary algorithm is a popular method for mining association rules. It works by identifying frequent item sets in a dataset and then generating rules based on these item sets. Apiary is widely used in retail and e-commerce to uncover patterns in customer purchases, helping businesses recommend products and design effective marketing strategies. ECLAT is another algorithm used for association rule mining. Unlike apiary, ECLAT uses a depth-first search approach to find frequent item sets. It's known for being faster and more efficient, especially with large datasets. ECLAT is commonly used in market analysis and recommendation systems, providing valuable insights into customer behavior. Association rules are used in many industries beyond retail. For example, they help in web usage mining to understand user navigation patterns, in healthcare to find relationships between symptoms and diseases, and in finance to detect co-occurring events. These applications show how association rule learning can uncover valuable insights from complex datasets. Anomaly detection is a technique used to identify unusual or unexpected data points in a dataset. In unsupervised learning, anomaly detection algorithms learn the normal patterns in data and flag anything that deviates from these patterns. This is crucial in applications like fraud detection, network security, and fault diagnosis, where catching anomalies early can prevent bigger problems. Isolation forest is a popular algorithm for anomaly detection. It works by randomly partitioning the data and isolating points that are different from the majority. Anomalies are easier to isolate, so they require fewer partitions. Isolation forest is efficient and effective, making it a common choice for detecting outliers in large datasets. One-class support vector machine, or one-class SVM, is another method for anomaly detection. It learns the boundary that separates normal data from potential anomalies. One-class SVM is especially useful when we have a lot of normal data but very few examples of anomalies. It's widely used in fraud detection and intrusion detection systems. Autoencoders can also be used for anomaly detection. By training an autoencoder to reconstruct normal data, we can measure how well it reconstructs new data points. If the reconstruction error is high, the point is likely an anomaly. This approach is effective for detecting unusual patterns in images, time series, and other complex data types. Anomaly detection is used in many real-world scenarios. Banks use it to spot fraudulent transactions, while network administrators rely on it to detect cyberattacks. In manufacturing, anomaly detection helps identify faulty products before they reach customers. These examples show how unsupervised learning keeps systems secure and reliable. Unsupervised learning comes with its own set of challenges. Since there are no labels, it's often hard to evaluate the quality of the results. Choosing the right algorithm and tuning its parameters can be tricky. Additionally, unsupervised learning can be sensitive to noise and outliers in the data. Despite these challenges, it remains a powerful tool for discovering hidden patterns. Evaluating unsupervised learning models is different from supervised ones. Since there are no labels, we often use metrics like silhouette score, Davies-Bouldin index, or visual inspection to assess clustering quality. For dimensionality reduction, we might look at how well the reduced data preserves the original structure. Evaluation is crucial to ensure the model's results are meaningful and useful. Selecting the right unsupervised learning algorithm depends on the data and the problem at hand. For example, clustering is great for grouping similar items, while dimensionality reduction helps simplify complex data. It's important to experiment with different algorithms and evaluate their results to find the best fit for your needs. Data preprocessing is a crucial step in unsupervised learning. Cleaning the data, handling missing values, and scaling features can greatly improve algorithm performance. Good preprocessing ensures that the algorithms can focus on the true patterns in the data rather than being distracted by noise or inconsistencies. Feature engineering involves creating new features from raw data to improve model performance. In unsupervised learning, well-designed features can help algorithms uncover more meaningful patterns. This step often requires domain knowledge and creativity, as the right features can make a big difference in the results. Scalability is an important consideration when working with large datasets. Some unsupervised learning algorithms like k-means scale well to big data while others may struggle. Choosing scalable algorithms and optimizing their implementation ensures that your models can handle real-world data volumes efficiently. Interpretability refers to how easily we can understand the results of an unsupervised learning model. Some algorithms like clustering provide clear groupings, while others like deep autoencoders can be more complex to interpret. Improving interpretability helps build trust in the model's results and makes it easier to act on insights. Visualization is a powerful tool in unsupervised learning. Techniques like scatter plots, dendrograms, and Teosini plots help us see patterns and clusters in the data. Good visualizations make it easier to interpret results and communicate findings to others, especially when dealing with high-dimensional data. Sometimes, combining multiple unsupervised learning algorithms can yield better results. For example, you might use dimensionality reduction before clustering to simplify the data, or combine clustering with anomaly detection for more robust insights. Experimenting with different combinations can help you tackle complex problems more effectively. Semi-supervised learning is a hybrid approach that combines labeled and unlabeled data. It leverages the strengths of both supervised and unsupervised learning, making it useful when labeled data is scarce but unlabeled data is plentiful. Semi-supervised learning can improve model accuracy and make better use of available data. Transfer learning involves using knowledge gained from one task to improve performance on another. In unsupervised learning, transfer learning can help when data is limited or when we want to apply insights from one domain to another. This approach is increasingly popular in fields like natural language processing and computer vision. Self-supervised learning is a special case of unsupervised learning where the data provides its own supervision. For example, a model might predict missing parts of an image or sentence. Self-supervised learning is gaining traction in deep learning as it allows models to learn useful representations without labeled data. Deep learning has expanded the possibilities of unsupervised learning. Neural networks can learn complex representations of data, enabling powerful techniques like deep clustering, autoencoders, and generative models. These advances are driving progress in fields like image recognition, natural language processing, and beyond. Generative models are a class of unsupervised learning algorithms that can generate new data similar to the training data. Examples include generative adversarial networks, GANs, and variational autoencoders, VAEs. These models are used in image synthesis, data augmentation, and creative applications like art and music generation. GANs, or generative adversarial networks, consist of two neural networks competing against each other, a generator and a discriminator. The generator creates new data while the discriminator tries to distinguish between real and fake data. This competition leads to highly realistic generated data, making GANs popular for image and video synthesis. Variational autoencoders, or VAEs, are another type of generative model. VAEs learn to encode data into a compressed representation and then decode it to generate new samples. They're widely used for generating images, text, and even music, thanks to their ability to model complex data distributions. Unsupervised learning plays a big role in natural language processing, NLP. Techniques like word embeddings, topic modeling, and clustering help computers understand and organize text data. These methods power applications like search engines, chatbots, and document classification. In computer vision, unsupervised learning helps organize and interpret images without manual labeling. Clustering, dimensionality reduction, and generative models are used for tasks like image segmentation, object detection, and style transfer. These techniques make it possible to analyze vast amounts of visual data efficiently. The future of unsupervised learning is bright, with ongoing research pushing the boundaries of what's possible. Advances in deep learning, self-supervised learning, and generative models are opening new doors in AI. As data continues to grow, unsupervised learning will play an even bigger role in making sense of the world around us. Wrap up: unsupervised learning algorithms are powerful tools for discovering patterns, reducing complexity, and generating new data. From clustering and dimensionality reduction to anomaly detection and generative models, these techniques are transforming industries and driving innovation. By understanding the strengths and challenges of unsupervised learning, you'll be better equipped to harness its potential in your own projects.